Okay, so fluid dynamics describes the flow of fluids, and it's very important in volcanology. This is obvious when magma erupts and lava, the flow of lava determines its impact and its spatial distribution. But as we've just heard in the previous talk, it's also very important for the magma flow in the plumbing systems. In particular, the fluid dynamics inside dikes it affects the way crystals grow, the signals that dikes may give off, and also its eruption potential. So yeah, but obviously we don't really know what's happening inside there. It's naturally hidden from view. So today I'm going to talk about insights about the fluid dynamics of dikes that we can get from analogue experiments. So yeah, I'm Caitlin, and this work is part of my postdoc at the University of Liverpool, which I'm doing with Ginny Kavanagh. So shown here is a dike in two orientations: in the plane of its thickness, where it opens against the rock, and it's the plane of its breadth, where the fluid can spread laterally. And we consider dikes that are driven by an influx of fluid, where they are initially driven by the pressure from the injection. They may eventually become buoyant once enough fluid has been injected, but this isn't always the case. So these dikes are driven by the pressure of the magma fluid, but in turn, the pressure is affected by the fluid flow. And we can characterize the fluid flow by the Reynolds number, which is a dimensionless number that measures the ratio of inertial to viscous forces. So the viscous force represents the resistance to shear deformation of the fluid, and it resists motion. Whereas conversely, the inertial force drives flow and adds momentum to the flow. So low Reynolds number typically represents like a really slow viscous creeping flow, whereas high Reynolds numbers is more representative of a really high velocity flow, which may become turbulent and have turbulent eddies. But dikes have a wide range of flow conditions. The viscosity of magma and the velocity of magma varies widely. This is an estimate from the literature of the Reynolds number in dikes, so it ranges from very, very small to around numbers around 1,000, and that's calculations predict that dikes may become turbulent at Reynolds numbers of 1,000. But yeah, this is generally this assumed to be quite viscous dominated, and that makes sense because of the thin geometry of dikes. But so in dike models, which are essential for interpreting the signals and trying to predict how a dike will behave, the dikes are always assumed to be viscous dominated, and as a result, we also assume that the flow is unidirectional. And this has important implications for then how your model is derived, but it's not always the case. And also these models are derived on a steady state, a dike that's already reached a steady state of propagation and is buoyantly propagating. But in nature, dikes aren't always viscous dominated, and they're not always unidirectional internally. So we investigate this using our analog experiments. So shown here is a schematic of our analog experiments where we inject a Newtonian fluid, which is a magma analog, into transparent gelatin, which is an analog for the elastic host rock. And the fluid is seeded with tracer particles, and we illuminate the plane of the dike growth with a laser sheet. And when illuminated, these particles fluoresce, and then we record them with a camera so that we can then view how the fluid is moving and what the internal motions look like. So we create a range of Reynolds numbers in the lab by varying the fluid that we inject. So it's always Newtonian, but we use low viscosity fluids, water, and also a glycerol solution. And we also use a very high viscosity, relatively high viscosity fluid of silicon oil. And we inject these at different rates, shown here in terms of rotations per minute that our pump allows, to create a wide range of different flow conditions. So in our experiments, we achieve Reynolds numbers of the order of 10 to the minus 2 to 1,000, so kind of representing the upper range of Reynolds numbers that we may expect to see in natural dikes. Here's a photo of our laser in action with Janine in the background. And this here is our laser, which we've named Medusa, because you shouldn't look either of them directly in the eyes. This is an example of an image that we obtained from our recording. So these are the fluorescent particles that we can see and track. And we apply an optical technique to these images called particle image velocimetry, or PIV, which just can track groups of particles between two subsequent frames and obtain instantaneous velocity fields. So this is an example of a velocity field within our dike, shown in the plane of the breadth of the dike, where the arrows show the direction of flow and the colours represent the magnitude of the velocity. So we use these experiments to try and understand more about fluid dynamics, but in particular, we want to answer some questions such as, how does the internal fluid behaviour relate to the overall propagation velocity of the dike, which in nature is the signal that can be measured in natural dikes as opposed to the velocity of the internal flow. We also want to know what the fluid dynamics look like at different Reynolds numbers. So is it always unidirectional? And also I should mention that our experiments are always flux driven. The dikes don't become buoyant. And finally, when are inertial effects important? Because as I mentioned, these are always neglected in dike models. So shown here is the plot of the Reynolds number against the dike tip velocity. So as I mentioned, the Reynolds number is the ratio of inertial to viscous forces, which can then be written as shown, where we have the density, the dike thickness, the characteristic velocity divided by the viscosity. So yeah, you can see our range of Reynolds numbers on the x-axis, where our characteristic velocity we obtained from our quantitative PIV data. So we can see that there is clearly a defined relationship between the internal Reynolds number and the dike tip velocity. But also we can see that there's quite a wide range of dike tip velocities a wide range of Reynolds numbers for around a constant dike tip velocity, which we thought was quite interesting because there could be lots of different things happening inside, but then the dike is moving at the same rate. So here's what the flow looks like for all of our experiments that we conducted. So we have the silicon oil ones on the top, and the glycerol and water experiments on the bottom, with the Reynolds number shown at the top. So the silicon ones are quite viscous, have very low Reynolds numbers, but what we can see in that every single experiment, the fluid recirculates. There's a region of high velocity, a centralized high velocity jet just above the injector, which then once that the fluid reaches the dike tip, it then recirculates and spreads laterally. And this this distributes the pressure so that the dike can grow laterally as well as just upwards. But although they all recirculate, you can see that there are actually different degrees of recirculation for each experiment. So to understand a bit more about the dominant forces, we can look at the Reynolds number in a bit more detail and plot the Reynolds number against the volume flux of the fluid. So as you can see here, there are two Reynolds numbers for each experiment. And that's because, as I mentioned, in nature, it's the tip velocity that's often like the relevant and measurable parameter as opposed to the internal fluid velocity. And people often will estimate the Reynolds number of a dike using that tip velocity. So here I've plotted two Reynolds numbers, a PIV Reynolds number where we've used the velocity from our measurements that we obtained internally, but also a tip Reynolds number where we use the tip velocity. So firstly, you can see that if you use the tip velocity, you always underestimate the Reynolds number because the fluid is always flowing much faster, quite significantly faster in general than the tip. So that's why it recirculates, because the fluid is going faster than the dike, so it has to go laterally. It has nowhere else to go really. So, but we can also use this relationship between the two Reynolds numbers to understand more about the difference between the inertial, viscous and inertial forces, and when inertia might be important. Let's first of all focus on the high viscosity silicon oil experiments. So as we increase the flux, after a while, the Reynolds number tends to a constant value, and we essentially can't add any more inertia to the system. because of the viscosity, viscous effects are very significant in this experiment. The Reynolds number is always less than 1, which tells us viscous forces are always dominant. And as we increase the flux, we increase the shear in those systems. So we actually increase the amount of shear resistance. So we can see this in our flow patterns, in that as we increase the flux, although the dike's moving faster, the degree of recirculation actually reduces because there's more viscous resistance occurring within the flow in general. Conversely, when we look at the less viscous fluid, we always, for the parameters that we've used, when we increase the flux, we always obtain like faster and faster flow. So because viscous resistance is not that significant in these experiments, when we increase the flux, we only act to accelerate the internal fluid more, essentially adding more inertia and more momentum into the system. And we think it's quite a dominant force in these experiments, and it is important. So this suggests that inertia, whether or not inertia is important, depends on the viscosity of the magma. So thank you for listening. Just to summarize, we've shown that recirculating flow is always present in Newtonian dikes, which has very important implications for the nucleation and growth and distribution of crystals, which are very dependent on the pressure distribution, which is affected by the flow. The effect of inertia, whether or not it's important, depends on the viscosity of the magma. And there's also a very clear relationship between the flow dynamics and the dike propagation velocity, but it's not like a linear relationship, and there's different flow conditions can result in the same tip velocity. And finally, these experiments, the fastest flow we were able to create with the largest Reynolds number had a Reynolds number of around 1,000, and this was the highest setting of our injector. So we couldn't really create a faster dike than this. So this is like on the cusp of what is predicted to be the Reynolds number that allows turbulence in dikes. But this isn't turbulent because turbulence is characterized by like chaotic flow and non-structured flow. This has a very clear defined structure. So we haven't achieved turbulence yet, but it's something that we're interested in. Like, can dikes ever become turbulent, the fluid flow in dikes, and what would that look like? So yeah, thank you.